All right, so today is the ninth recitation, and today we're going to go over just a general high-level LQR overview roadmap. I know over the semester we've gone through a bunch of different variants of LQR, and it can be a little bit confusing, so we'll just kind of go through when to use which and what they actually do and what the alternatives are if we're given a certain problem. And then we'll do just one quick run through of how we discretize systems. So we had some issues with this on the last homework where people were discretizing or linearizing their nonlinear systems in a way that was a little bit weird. And then the largest part of today's recitation will be going over sparse trajopt. So this is something we haven't done in the class yet, or I guess we haven't made you do in a homework yet, but it's probably going to be really nice to know for the project itself. And it can take, the time it takes to solve your problem from being like 10 minutes to being like, 30 seconds or whatever. So just, I provided a bunch of stuff for you that I'm going to go through today. And I'll kind of walk through how to actually use it, how to download it, and how to get started. And then hopefully you can just take an example that I give you and then tailor that to your specific project. So that is the idea, is that we want to give you guys solvers that are very easy to use, such that you can spend time doing cool problem stuff and not worrying about how to interface with these existing solvers. All right, so with that, and then also I think this will be probably shorter than an hour. So any like other questions and stuff, we can always go through at the end. So the first thing is an LQR overview or roadmap. So I'm just going to write down all the different LQR terms that we've heard. And then if there's an LQR term that you've heard that is not on this list, speak up, and then I'll add it. And then we can go through everything. So we've heard infinite horizon LQR. We've heard finite horizon LQR. Time varying LQR. And then I LQR. And then, yeah, I guess this is probably appropriate. But are there any, I guess, LQRs that I can't remember that we've mentioned? Because a lot of these are similar when it comes down to how we actually name them. But I think should be all encompassing. So let's start with, I'll just write it here, the list. So here are the LQRs. So the first thing we do is, I guess I'm gonna make a little like chart here as to when we actually use which of these and what they actually do, just to remind them. So infinite horizon LQR, so the first assumption for everything, the exception of one, is linear dynamics. I will do linear. Actually, I'll be even more general. I'll just say if it looks like this, we got some options. So on one hand, I'm going to say yes, no. And then, let's see, run forever. So the next thing is, are we running this thing forever or are we running it for a specific trajectory? So some examples of this is if I have a refrigerator and I have a temperature control on this thing, that's going to run forever. That's not just running for the next hour, that's running forever. And so I can design what I can call like a regulator to just run this thing forever. So if I am in fact running this thing forever, then I will use infinite horizon LQR. And this is where, we have min or ooh, min 1 through infinity, u through infinity minus 1, which is obviously not real, but humor me. And then I just have this infinite sum of our cost. And I'll just do. So this is our infinite horizon LQR, and this is what we solve with the Riccati recursion, or there's other methods. But what we did is that this is when Zach goes and derives like the dynamic programming solution. If you keep that thing going forever, it'll converge on a steady state K. So this we solve with Riccati, and we get 1K. So we solve this with Riccati, we get 1K. This is our first and arguably most useful of the LQRs. Now, if I'm not running it forever, then I have time varying LQR, which is the exact same as finite horizon LQR. And the only difference between these is that time varying implies that I have different A's and B's for each time step, and finite horizon just implies we have the same A and B. So I'll just go ahead and take the same problem. I'm doing min, and this time I'm doing 1 through n, and u 1 through n minus 1. And then my cost function is our normal 1 n minus 1 u plus and our terminal cost. Go ahead and write this out a little clearer. Here's our stage cost. And then subject to, and I'm gonna ignore the initial condition constraint for all these things, but they all have initial condition constraints. And what I'll do here that I didn't do before is I'm gonna add a little K for the time step for the matrices. So basically, if I have A's and B's that change at the time step, so they're actually a function of K or a function of time, then this is time varying LQR. But if A and B are just constant with no K, then I have finite horizon LQR. But it's the same algorithm either way. And this is what we did a bunch of in homework 2. The one where we had, I think, question 1 of homework 2, where we had a bunch of solve this with Riccati, solve this with convex optimization, show they're the same. And our two options here is solve with Riccati for K 1 through n minus 1, or solve with some convex optimization solver for x's u's. And the last thing is that if I have nonlinear dynamics, then I have to use iterative LQR. And this is where I just have a generic 1 n minus 1, oops, 1 to n, then u 1 to n minus 1. Then I have, some stage cost, and then some terminal cost. I'll try and scoot this over. And then most importantly here is that now I have generic nonlinear dynamics. So before, and then we solve with LQR. It's like kind of the name of a problem and the name of a solver, I guess. So this should, I guess, in some way put it like in your head as to where to actually place these things. So the assumption is linear dynamics and no constraints. So I will add asterisks here. No constraints other than initial condition and dynamics. So those are the two constraints I can handle. I can handle the initial condition, which is just x naught equals x naught, and then the dynamics constraints. But any other constraint, I'm not going to consider with these. So this is input constraints, so bounds on u, or is it going to be state constraints or collision avoidance constraints? Whatever it is, I can't solve with this. So these are the LQRs. If I have linear dynamics, I'm running forever, I use infinite horizon LQR. If I'm not running forever, I'm doing like a finite trajectory. This is where I use time varying LQR. And if I have a nonlinear system that is also finite, actually I'll do, this is just assumed to be finite. Then I use ILQR. So I guess here is the family of the LQRs. And then as soon as we add any constraints, we have to use other stuff. So if we add any constraints, it's convex trajopt. If we add constraints and it's nonlinear, then it's going to be non-convex trajopt. And then I think what's like a really important distinction to make is, so a few things. One, if I add constraints, I have to use convex trajopt. And if I add constraints plus nonlinear dynamics, and I do non-convex trajopt. And actually, I'll just go ahead and add this in a, what color should I use? I'll use a green. And I'll say that these are, that looks terrible. These problems are convex, and this problem is not. All right.
Um, you mentioned that for nonlinear dynamics, we'll use ILQR. How is that different from using TVLQR and linearizing inside the for loop as we did in homework 2?
So in
So
Homework
we
2,
use
what we
TV.
did,
Yeah, yep, yep.
so in Homework 2, what we did is that we linearized our system. And then with that linear system, then we used time varying LQR. But
Right.
the problem we were solving had linear dynamics because we had just linearized our system. With ILQR, you do not linearize your system. You hand it your full nonlinear dynamics.
Okay. So the Taylor expansion is just for the cost function, right?
No, so the Taylor expansion we did was for the dynamics. What we did was that we turned, so this is in homework 2, I think question
Uh,
2.
no, in ILQR, the Taylor expansion is for the cost function, not the
Okay,
dynamics.
sure. So
Oh.
inside ILQR, when we're actually solving ILQR, inside that solver, we take Taylor's expansions of both the dynamics and the cost. The dynamics get expanded to second order, or sorry, the dynamics get expanded to first order, and the cost gets expanded to second order. But right now, I'm not talking about how these problems are solved. I'm mainly just talking about when to use what. But yes, you're right. Inside the LQR solver, we are doing, a bunch of linearization. And this is true with everything. Basically, like, because linear things are the things we can solve, every nonlinear routine out there is going to always reduce down to a sequence of linear things. So this is why, like, within LQR, it ends up being a bunch of linear stuff. Within a non-convex optimization solver, it ends up doing a bunch of linear stuff.
Hmm.
Linear stuff is that's what we can do reliably on a computer. So we always want to like boil these algorithms down to just do a lot of linear stuff.
When,
But
yeah, when
uh,
do you want to choose whether or not you go through the ILQR solver and have that do the linearization versus linearizing on your own and putting it through a convex chat job? Like, how do you know
Basically,
which one to do?
if you can get this, if you can get this to work, you should always use this. So if you have a
Okay.
system and I'm tracking a trajectory, I can linearize about that trajectory because I know exactly where I want to be at every single point. So basically, my linear approximation on the tracking problem is very good because I know exactly what my states and controls are going to be. And my first order Taylor series of my dynamics is very accurate. LQR solves much harder problems. So this is where I'm not just tracking something. I want to do like a cartpole swing up or something. And I basically need to solve for the control sequence that does that. So really, you should use these for tracking problems where I can track a nonlinear system by linearizing it in a local trajectory. And then LQR, I don't have to assume that. I can just solve straight up traj-opt problems with LQR. So this is for tracking. This is for general traj-opt. Does that make sense?
Yeah. And then my other question is about the terminal constraint. So because you're adding a terminal cost, you're driving the system to that end goal, but we also were adding our own like terminal constraint saying that we had to equal like the last step of the, how is that different? Or like where would you add that in, or do you technically not need it?
So in this case, in all these scenarios, I don't have any terminal constraints, right? I only have terminal costs. Like,
Okay.
so the assumption I made was that the only constraints I have are initial condition and dynamics. I do not have a terminal or a goal constraint. So what that means is that I won't be exactly at the goal.
Okay.
And so what you can do is you can make a very large terminal cost to like
Gotcha.
strongly encourage your trajectory to reach the goal, or I can
Hmm.
add a constraint. And what you see in the homeworks is that if I add the constraint, this terminal cost doesn't do anything for me because I've already
Yeah.
constrained it to be equal to the goal. So having
Yeah.
a terminal cost and a terminal constraint mathematically is redundant, but as far as the way the solver works, you should always have a terminal cost.
Gotcha. Okay.
Because if you remember when we did, like, especially for like LQR, is that when we initialize our problem for the backwards pass, our big P, little p, we initialize them with the terminal cost. So that's how we start the
Right.
regression. So it's just like, it's even if we have a constraint in there and we're using a Riccati-based thing, it's always worth having a terminal constraint in there. But
Right.
it's important to know that like if I, sorry, terminal cost in there. But it's important to know that if I have a terminal constraint that says, hey, the X at the last time step must be equal to this specified goal state, then the terminal constraint, terminal cost, wow, the terminal cost does not do anything to the problem. So
Okay. Thank you.
I'll add a note right here. So if I add a terminal constraint, so if I have a terminal constraint, the terminal cost, which is this ln thing, it does nothing for me, but I should still keep it. That's the takeaway. Okay, and then, so are we all good on everything LQR? We understand the LQRs. And now I will do one last thing, which is, so I've seen people kind of try and reconcile like when do we use MPC, when do you use LQR? I think it's really important to separate these ideas. There are the LQRs that solve the problems as we just specified, and MPC is not tied to any specific type of problem. MPC is just the idea of solving a traj-opt problem in a loop. So MPC is anytime I have, if here's my simulation. If I'm doing some simulation, and I do, U, so to write it out in code, MPC is anytime I do this, this is MPC. It just means that in my simulation loop, at my control step right here, it just means I'm solving a traj-opt problem. So it could be any of these. I could use LQR for MPC. I could use time varying LQR for MPC. Even use this, I guess, if I want to like linearize a different system. But whatever it is, if I'm solving a trade-off problem at every single time step for a new control and executing that first control input from the solved trajectory, that is MPC. So it's not like, do I use MPC or LQR? It's important to know that MPC is kind of abstracted away from these things. And it's the general approach to control where I'm simply solving hopefully small trade-off problems as the controller itself.
So can we throw in a non-convex optimizer inside an MPC,
Yeah,
like
so
the recall?
there are people who do. So what's most common is to use something like an ILQR based thing. So remember, ILQR is non-convex. And
Right.
people use ILQR for MPC. They will solve ILQR problems at every single time step and keep solving. There are also people who solve direct collocation problems as an MPC thing, which is like a little more tricky to pull off, I guess, in terms of the software difficulty. But yes, people do at this time step right here, people do in fact solve crazy non-convex stuff. So Boston Dynamics for Atlas locomotion, they are solving a version of a non-convex problem at every time step.
Okay, so from my understanding, like we do MPC inside the loop. So basically, we do the convex traject inside the loop so that it acts as a feedback controller. But in case of ILQR, we already have the gain. So what would be the reason to solve an ILQR inside a loop in an MPC approach?
So this is a good point. ILQR, it gives you a set of feed forward U's, and then it also gives you a set of X's, and then it gives you a bunch of K's, right? So ILQR gives you a bunch of feedback gains. Those feedback gains help you track the given trajectory. So if all you want to do is track the trajectory, then you don't need to resolve the ILQR problem. You already have the gains to do so. But what's more common is that like either my linearization is changing dramatically, or I'm taking a new route, or things change online about like, I'm moving to one side of the obstacle versus the other. So if I do feel like I have to resolve the problem because the assumptions I used when I first solved my ILQR problem are poor, I will resolve ILQR. But the point that you're making is totally valid. If I'm just tracking a reference that I created with ILQR, I don't have to use MPC because ILQR gives you a feedback controller for free that tracks the X's and the U's.
Right. Okay.
All right, so now let me try and think of the
Would,
best way to do this. So now I'm going to do, I guess I'm going to,
would you ever, sorry, this is about NPC really quick. Would you ever roll forward your finite horizon? Like the next time step, you would look an additional one step farther and like, or you know what I mean? Like, would you ever, or is that what it's doing? Is it always you had like a finite horizon of like 50 time steps and you solve all 50 and then take the first step? Do you solve the next 50 or is it solving the next like 49 until
okay,
you
yeah,
get to the end of the, yeah.
this is a good point. So let me draw a little timeline. So say I'm at this time step right here, and my MPC window is solving this. So at this time step, I solve, I'll use this color. When I'm at this time step, I solve an MPC problem for this sort of window. And then I'm at this time step, and you just shift the window over. So it's not like you solve the first 50 and the second 50. This window is sliding as you slide. So do you see what's going on here?
Yeah, this
Then
makes more sense. Yeah.
what happens when you're reaching the end? Like say you're reaching the goal and the goal is just 50 steps away.
Mhm.
So in the next step, will you do 49? Because if you do 50, then you will kind of tracking ahead of the goal. You're kind of overshooting.
So in general, you really don't want to change the size of the problem that you're solving online. You want to solve the same sized problem. So in that case, if I'm reaching the goal after 50 time steps, This is what you guys did in your homework for the rendezvous with the SpaceX Dragon. When we did that rendezvous, we used the same size window every single time step. And all we did was that we said that once we reached the goal, we just kept the goal as our desired position. So do you remember doing this in question 3 of homework 2?
Yes, but I think I did not pay attention to this fact that we were keeping it constant.
Yeah. So
So,
basically what you do is you just like augment
okay.
any sort of post-goal activities with just stay at the goal. And so that way we can keep our NPC problem the same size. What you're talking about is a little tricky to pull off because you have an NPC window that is shrinking. Like you start here and then you just shrink until it's nothing. The issue with that is that like when you allocate a solver to solve online, like on hardware, I want that to stay the same size. I don't want to have to reallocate a new problem instance for a larger or smaller problem. So yeah, if you have this question, you should totally look back at what you did in homework 2, question 3, and look at how we dealt with that because that was like we were rendezvousing and we were docking with something, but the size of the problem was the same. So what that meant is that like a time step before I docked, I was considering one more time step, and then the rest of the time steps were after docking was done. And it's very easy to deal with that in a way that the solver won't complain about.
Okay, so but we'll still be calculating for ahead of the goal, but we won't be executing it.
Exactly.
Ah, okay, got it.
Okay, so I guess I won't spend that much time on discretization. I will just say the following thing. So I'll just say, I will say that I will say the following thing. So do you guys remember the linearization warm-up that I put in a few of the homework questions? So when in doubt, consult that. And this was in, I believe, I'll go ahead and change this if this is wrong afterwards, but I believe this was homework 2, question 2, is I think we're tracking the carpal swing up. I'm pretty sure. So when in doubt, consult this. Make sure you really understand what goes on in those few lines. And the second thing is matrix exponential. So the matrix exponential has exactly one use. So when do I use the matrix exponential? It is when I have okay, so the exactly one use of the matrix exponential, and that is taking linear systems, so not linearized system, linear system. So I'll make this like extremely important. So linear systems, not systems that have been linearized. So there's a very important distinction here. For linear systems, I use the matrix exponential, and this gives me my discrete time system. But do not use this once you linearize the system, especially one that is moving in time. But just when in doubt, don't do this. Instead, what I want to do is if I want to so I'll do discretize. Here's like a discretization flow chart. How do we discretize nonlinear or systems in general? So, or I should do. Okay, so is the problem linear? If the answer is yes, then we do Actually, I will do a little more specific. So linear, and then so linear, no. Time varying, no. Then we use matrix exponential. Or sorry, this is yes. A linear system that is not time varying. So a linearly time invariant system, then I use matrix exponential. Anything that's not that, I linearize, I discretize with an integrator. So I'll do and this is really important because people made this mistake on the I think homework 2 now is that in order to linearize their nonlinear system, they were taking a continuous linearization. So actually, I'm gonna spell out exactly what not to do. So I will do and I'm gonna write this entire thing out in red so people don't do this. I like could not make this any more clear. Do not do this. Take and then approximate this with what else will do? So what you should not do is you should not take a nonlinear system that is in continuous time, linearize it to get a continuous time linearized model, and then take that linearized model and then use the matrix exponential to get AAC or to get AD and BD from AC and BC. You should not do this. What you should do is the following. So what you should do is you should discretize it. So discretize it with RK4 or anything. So this is a pretty important point that we saw a bunch of people do in the homework. If I want to discretize, if I want a discrete time linear system from a nonlinear system, so I want to linearize it in discrete time, what some people were doing was they were taking their continuous time system and they were forming the continuous time Jacobians, and they were using those continuous times Jacobians with a matrix exponential to get the discrete time stuff. And that you should not do. This is more complicated and it's more difficult and it's less accurate. What you should do is very simple. You should just always discretize your system like this, and then just go ahead and just linearize that system itself. So it's very straightforward. Whenever, like, we never want to take these Jacobians. In this class, everything that we've taught you so far, we are not using continuous time anything. So we are never trying to linearize continuous time stuff. We are always trying to linearize discrete time stuff. So the first step is always to discretize. So if I have a nonlinear system, go ahead and discretize it with RK4. This is what we do in all the homeworks. We discretize it with some explicit integrator. And then if I want to form a linear approximation of my discrete time system, I would just simply take those Jacobians. So hopefully the way I wrote this down kind of like really demonstrated that this is really easy and it's correct. So we should always do this. This can be very inaccurate and is more complicated and more expensive and slower and more lines of code. By every possible metric, this is a worse thing to do, but people still do this. Like you will read papers where people will do this, and it's crazy to me because this is like could not be any more objectively worse. And I think the main reason why people do this is because oftentimes computing these Jacobians by hand is actually a little simpler. Like I can write out my ODE and I can take my derivatives A and B by hand, but I can't really diff through an explicit integrator by hand. But we live in 2024 and there's amazing auto differentiation tools like forward diff. So we should not be afraid of taking Jacobians anymore. We can take these Jacobians through the integrator, whether it's RK4, RK8, RK3, Euler, midpoint, whatever. I can form these Jacobians, no problem. Don't be afraid of Jacobians. So I just say like one more time, always discretize first and then linearize. Never linearize, then discretize. I'll just do this. So first discretize, then linearize. If you ever find yourself doing this in a different order, you've done something wrong. You should come talk to us. Does this make sense? Yeah.
Does this apply for something like when we were taking the gradient and the Hessian of our like stage costs and stuff? Because I did do that by hand and then just like put it in the code. Is
So
that
in that
okay?
case, for the stage cost, there's no time
Yeah,
aspect, right? I'm
true.
just
Okay.
I'm just evaluating a function at a state at a control. So that's totally fine to do that by hand. In fact, I think you should do that by hand because it is so simple.
Okay.
What we're talking about here is dynamic systems. So things that functions that describe moving stuff. Okay. So discretize first, then linearize. This is very important. Okay, so with that, we have 20 minutes left. And so now I'm going to get into hopefully something that will be like very helpful for your projects. And that's sparse trajopt. So in general, at a very high level, I'll go over what sparse matrices are. So in a sparse matrix, just don't store the zeros, which seems pretty straightforward, right? Like I have a big matrix, I have a lot of zeros, don't store the zeros. Turns out that if there's only a few zeros, it's okay. Like you don't have to make it sparse. But if there's a lot of zeros, you should make it sparse. So like I'll give two examples here. So if I have like, zero, 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 like this is probably fine. This is probably fine to be dense. So basically if the number, so n z, this is number of non-zeros. So if I have a matrix where I have a lot, like my fill ratio on my sparse matrix, this is the number of non-zeros I have, the number of values. If I have a lot of non-zeros, I just store it as a normal dense matrix and everything is fine. If I have like a crazy pattern like this, like if I have like If I have a matrix that has some weird structure and it's very clearly sparse, then I should probably, and it has like, the number of non-zeros to the size is, 10% or something, then I should probably store it as sparse. So, so why does this matter? So sparse benefits. Or I'll just do like sparse pros and cons. So some pros and cons for sparse. Takes less memory. Faster matrix multiplication because I'm not multiplying a bunch of zeros together. I'm just ignoring those entries entirely. Faster linear system solving, which in turn leads us to faster optimization. Downside, um, I guess the way the matrix is stored is kind of weird. So actually, I won't, this is not important for us, so I won't say this. The only real downside I'll say is that like you have to specify the sparsity pattern. So basically, it's better in every way if it's very sparse, but now I have a sparsity pattern. And there's certain languages where that sparsity pattern can't change. So Julia is nice and very easy to use, and it lets us kind of change this sparsity pattern on the fly. But in general, we can't really do this. So this is, I guess, very quick, incomplete intro to sparse. I'm now going to switch to Julia and just go over some stuff and show you some stuff I've prepared for you guys to use for your projects. Okay, so we can all see my screen. So what I've done is I basically built this package called Lazy NLP QD. The idea is it's lazy nonlinear programming, like the quick and dirty version. And I basically am giving you guys two functions. One of them is called fmincon dense. This is the function that you've been using for your homeworks. And the other one is fmincon sparse, which is going to make a very big difference. So now I'm going to go through how to actually use this stuff. So here I have just a notebook that I'll put up on how we use this. And the idea is that if you're doing trad job for your project, which a lot of you are, you could just take this and swap in your stuff. And like you're now building off of something opposed to building it from scratch, which can make things a lot nicer. So activate our environment. Uh, I add the package using this. So it's not a registered Julia package yet. It's still just hosted on my own GitHub. So go ahead and we add it like this. Should take a second. And while this is loading, I'll get some other stuff ready, which is just done. Sometimes this stuff takes a long time. In the meantime, I'll start writing this stuff out. That done? Nope. Okay, now it's done. take a look at our package status. So I have, in this environment, I just have forward diff, and then I have my lazy NLP QD. Go ahead and load these. Now let's talk sparse matrices. Let's try and visualize these. So first, let's look at a dense matrix. This is a dense matrix. Every single entry has a bunch of stuff here. But I mean, they could be zeros, right? I could do like, D. They could be zeros, and I still store all the zeros. So I guess, okay. So here is a dense matrix. This is what we've been using all semester. Now what I can do is I can say, here's a sparse matrix, and I can specify a fill pattern of 0.1. And here's what this looks like. Now all the zeros are just not even there. So what I'll do is I'll do, so here's S, then I'll do a dense version. So here's the sparse version. Here's the dense version. Do you see how all we're doing here is we're just not keeping track of the zeros? And sometimes if it's very sparse, like there's few of these non-zero entries, it's worth it to do things in terms of sparse. It turns out that when we do trad problems, it's really, really worth it to do it like this. So now I'm going to go through the interface on how we actually use these solvers and what you would build on top of. So the first thing here is
So
this is
does
the
it
function
just
to create
ran?
a, sorry, go ahead.
I was just going to ask, does it randomly place those values
So in this
in?
case, because I am actually just randomly creating it, it does
Oh,
randomly create
gotcha.
them.
Okay. Okay.
So this last entry is a fill ratio. So fill ratio equals, so here I'll do 0.5, way more values, 0.1, fewer, 0.9, a bunch. So this is what the fill ratio means. So now let's create a random QP. I won't go into this. I will just say, if you want to take a look at this or talk to me about this, feel free. But what I'm doing here is I have my KKT conditions of optimality. I'm simply choosing some of the values and then solving for the other ones. And that gives me a QP that is solvable. Because I started with the optimality conditions, I know it's solvable. So anyways, this is just a way to create random QPs if you ever want to test a solver. Create random QPs. And now we have the dense fmincon. And this is the fmincon that you guys have been using for all your homeworks. So this is the normal form that this function takes, the same as your previous homeworks. And then now we want to solve the following QP. So we just put this into that form. So what we do is that, we convert to dense, just convert to dense. I specify a cost function, an equality constraint function, and an inequality constraint function. I put primal bounds on it. I put constraint bounds on it. I don't need this. Remove this. And then in this params, I just load it up with all the info that I need to evaluate my three functions. So this is, this should look very similar to what you just did on your homework using fmincon. Diff type, make it auto. Or if I want a finite diff, I can make this finite. And then here's I call it. I can just give it I give it my three functions. I give it my primal bounds. I give it my constraint bounds, my initial guess, params, diff type, and then tolerance, constraint tolerance, max iterations, and verbose. So I do this. It solves, and what you'll see here is that the number of non-zeros, so this is what I was talking about, and the equality constraint Jacobian is 300. And because this problem is 30 by 10, there's every single entry is considered non-zero in the eyes of the sparsity pattern. And the same is true with the inequality. So these are huge numbers, and these make the solve slow. So if it actually turns out that these are sparse matrices, it's worth doing it in a sparse way. This is the point I'm getting towards. So we see these numbers, 300, 600, solving for 30 variables. These numbers are pretty big. That means the problem is going to be relatively slow. So now let's do a sparse fmincon, and this is like, I guess what you'll be using. So now let's use a different NLP format. Let's say that I just want to constrain X to be within XL and XU. And then I have just my inequality constraint is just between CL, CU. So what does this mean? How is this different? So there's no specific equality constraint function now. All I'm saying is that if I want to make those things the equality constraints, I will just make CL and CU equal to the same value. So very straightforward. And then if I want to solve this QP, I'll go ahead and put it into the form. So here's the original QP, and here's me putting the QP into a form that accepts this right here. So the equality constraint, if I say it's between 0 and 0, it has to be 0. So this is my equality constraint right here. And then the inequality has to be less than 0 because that's what I specified, and then greater than negative infinity. So I know I'm speeding through this. I will upload this and you can take some time. You can go through it on your own and play around with it. But here is the form that we're using for our sparse fmincon. And here's just one quick example of how I turn this problem into the sparse fmincon style. So the way I write these functions is a little different and a little more difficult. And so what I'm about to say is that we have a much faster way to solve these problems, but we have to do a little bit of work to make our constraint and cost functions satisfy this and I guess play by the rules. So the cost function is the exact same. It's a normal cost. My cost gradient, I'm going to edit grad in place. So grad is an incoming vector. I'm going to compute my gradient and I'm going to store it into grad. And I return nothing. And then for the constraint, I do the same thing. I edit cval in place. So this comes in as a vector. I just assign the values of that vector to my constraint function. So before I was just returning the values. I was returning the cost, returning the constraint. Now I am basically taking the constraint value and I'm stuffing it in one of these vectors I got right here in this exact way that I'm doing right here. And then the constraint Jacobian, this is, what is the derivative of these two things right here with respect to X? So I see it's A and G. So my constraint Jacobian is sparse AG. And then the same thing as before, here are my primal variable bounds. Here are my constraint bounds. Here is my sparse Jacobian matrix with the correct sparsity pattern. So what's important here is that the sparsity pattern, so the zeros, non-zeros in my constraint Jacobian, it cannot change. It must be the same throughout the entire solve. So what I do is that to start the solve, I give it a sparse Jacobian. I say, this is the sparsity pattern that I'm going to be using the entire time. So what I do is I give this temp conjac. This is my sparse Jacobian matrix that contains my correct sparsity pattern. So in this case, my Jacobian is not changing even the values, let alone the sparsity pattern. So the sparsity pattern is locked from the very beginning. So this is how I communicate what that pattern is. And then the way I feed it is I feed it cost gradient, constraint Jacobian. And then I feed it I guess the ideal structure of what my sparse Jacobian looks like. So just compute it once, get the sparsity pattern, and just feed me an example of Jacobian. So just give me any example of this. And what we'll see is that before, when I solved this problem, this had 300 non-zeros in the equality and 600 in the inequality. And now I just solved the sparse version. Now there's 92 values in the equality and 185 values. So this is like a huge decrease in the amount of time this took. So this solved super, super fast, gives me the same solution, and I passed. So again, I'm running through this, but you should take some time and go through this later because you will probably use this for your project. And specifically, now let's do some sparse trajopt. So this example right here, this is the example I anticipate people will take and put their own system into and try and get their system working with this solver. And I think that's like a great idea. So here's how I specify that using all the rules I just set up. And here's like a full problem start to finish. So here is the dynamics. Here is the ODE of a cart pole. Here's our normal RK4, nothing crazy. This is the same create IDX function that I used in homework 3 that I gave you guys. So this just basically, if I have to put everything in a big Z vector, This is how I grab out the X's and grab the U's. Basically just like all the indexing stuff. And my cost, here I'm just using an LQR cost where I'm tracking an XREF, UREF. And here's my terminal cost. Cost gradient, I just use forward diff, but you should probably write this by hand. So and then for the constraint value, I have a few different constraints here. So for 1 to n minus 1, I have my dynamics constraints. This is me saying that xk plus 1 should be equal to rk4 of this. So here are my dynamics constraints. And just like you did in homework 3, I could put an explicit or an implicit integrator here, and it will work just fine for both these things. So this is where our dynamics constraints go. And then if you wanted to, you could put your initial condition and your terminal constraints here. But since we have primal variable bounds, we don't have to do this. We can just bake in those constraints in the primal variable bounds. And now is I guess here's the sparse matrix part. So for constraint Jacobian, I take in this conjac. This is a sparse matrix. So I guess I said that twice, so I'll delete that. So now I go through and just like I did with my functions, cval of IDX CI, this is conjac of IDX CI, I just take the derivatives of this with respect to the three values that show up here. So xi plus 1, xi, and ui. This is xi, ui, xi plus 1. I take these Jacobians right here and then return nothing. And now that's basically all I had to do to specify my problem. So now problem size, I have 4 states, 1 control, dt of 0.05, solving for a 2-second trajectory. LQR cost, here are my cost values. Indexing, initial goal is going to be the cartpole down, and final goal is cartpole going up. This is the exact same problem from homework 3. And then for my params, I just load in everything I need to evaluate my functions. So this is what I need to evaluate my cost functions. This shows up in the constraints. Basically, any value I need in any of the functions goes right here. Primal bounds. These are these are the xmin and xmax for values of x and values of u. And then if I'm stacking everything up into a big z vector, what I'll do is that I'll put in my initial condition constraint like this. And then I'll go through it and I'll set each element of z lower and z upper as umin, umax, or xmin, xmax. This is me setting my state and control constraints. And then my terminal condition constraint goes in here too, just saying that, okay, the nth x must be equal to my goal. And then for the constraint bounds, CLCU, these are zeros because my only constraints here are equality constraints. And then the way I initialize is dumb. I just go ahead and throw a random number in there, but you should really do something more clever. So here's how you do something more clever is you'd go through and you'd index into Z0 and you'd add like a clever initial guess. So here's how we initial guess. And then I'm going to evaluate this Jacobian once, and I'm going to get the sparsity pattern. And this sparsity pattern can't change. So I do temp conjac. This is my temporary constraint Jacobian. I initialize it as just a big blank empty sparse matrix. I go and I populate it with all my values by calling my constraint Jacobian function once. And then now I just feed everything to sparse fmincon. And even though this is like a relatively large problem, it solves like extremely quickly in very few iterations. So only 745 non-zeros, and I'm solving for 196 variables. So this is like significantly reduced in terms of size. And actually what I'll do is I'll show you what this looks like. So println. So here's a sparsity pattern of the constraint Jacobian. So this is how Julia shows very large sparse matrices. So this whole matrix, this is huge, but I only have values in like along this band right here. So before, when I use dense fmincon, I'm considering all these zeros and I'm storing this entire matrix and I'm inverting this whole matrix, and it's just like a huge number of wasted operations because there's so many zeros. But if I am clever about the sparsity pattern, I can specify where these non-zeros show up. And what I get is I get this huge matrix where it's basically empty. Like it's a very sparse matrix with very few entries. And this solves nice and quickly and gives us, here's our state as we swing up. Here's our control with the control balance. So I know I ran over a little bit on time. Basically, this tool is like going to be super nice for you solving on problems, and you could easily put in all of your own stuff. So from this template, it's very easy to go in here and like put in your own dynamics function, use your own integrator, change your cost to be whatever you want it to be, add whatever constraints you want to, and add the sparse constraint Jacobian the way you want to. All the pieces you need to build your own traject problem are here. And the huge benefit of this over fmincon is that sometimes fmincon is very slow because everything is dense. And by doing things in the sparse way, we can dramatically speed it up. I don't know if you could run this like MPC speeds, but definitely for like a class project, just like playing around with ideas, it's going to like dramatically increase the speed in which you can solve these problems. So I will upload all this. This package is like now available, and I'll be like sending out a note about this. And the idea is that this should be like super helpful for your projects. Okay, so with that, I will stop the recording.